Hi everyone. In this video we're going to continue on with the binomial distribution, and now we're actually going to look at the distribution itself, not just a binomial experiment. Right? So in that experiment that meets the four criterion that you need to be a binomial experiment, what we're usually going to be interested in is the number of successes out of the n trials. Because you really have a choice of what you can label as a success, and generally whatever you're interested in answering, you're going to label as a success. And so we're interested in the number of successes out of n trials. And that is important because that's how we're going to define a binomial random variable. We always use capital Roman numerals, usually x, y, and z, to represent random variables. And so x represents a random variable where it's counting the number of successes out of n trials. And if it's doing that in an experiment that meets those four criterion, then we call it a binomial random variable. Okay, so it's counting the number of successes out of n trials. Great. So, as an example of just quickly me writing down what that random variable would look like, consider the experiment of flipping a fair coin 3 times and let x count the number of heads. So we've had some experience with this. Actually, I might have done this in a previous section when we were talking about random variables generally. But flipping a fair coin 3 times, I get 8 possible outcomes. Heads, 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 and then so on and so forth. Heads, heads, tails, heads, tails, heads, all the way down to tail, tail, tail. Okay? And so the random variable x is going to go through each of these outcomes in the sample space. So this is sample space S, and it's going to count how many heads I see. So possible values of x here are 0, 1, 2, and 3. Right? So if it looked at this first outcome, this one, it would say, well, I'm counting 3 heads. And so the x would be 3 there, right? And then 2, 1, and then all the way down to 0. And so that's what the random variable would look like, okay, if it's counting the number of successes out of n trials. Okay. Next, we're actually going to look at the distributional form now. So I'm going to show you a number of things that are, I'm going to format this slide rather to show you certain things that I'm going to show you about all the different distributions we're going to learn about. And the first one is the parameters. Now, if you remember back to the beginning of section 3.3 videos, and really it's at the end of section 3.2, we talked about the parameters or the parameter of a distribution. It's something that defines a distribution to be sort of what it is. And it's also why I refer to the binomial distribution as actually a family of distributions. Because a binomial distribution has a sort of general form where I have parameters or variables in them, and then every time that I plug in or substitute in different numbers for these parameters, I get a totally new distribution. Anyway, the two things that define a binomial distribution, and a fancier way to say that is parameterize a distribution, are the number of trials, so how many trials I do, and the probability of success for each trial. So the binomial distribution has 2 parameters that define it from any other binomial distribution, and that's how many trials you are doing and the probability of success for each trial. With those things in mind, how we denote a random variable that has a binomial distribution looks like this. Okay? And we have not seen this before, so I'll take some time to actually talk about it. We always put the random variable to the left. So the thing in the middle is called a tilde. 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 If you look on your computer, it's on the top left, usually, of your keyboard. Okay, so top left of your keyboard, at least for me it is. It's called a tilde, and so just in words, I would say x tilde, and then I've got some stuff on the right side. We always put the random variable on the left, and we say x is distributed. So that's what the tilde means, is distributed. Or it has this form. It is distributed. And then any binomial distribution, you're going to put in this spot in between the parentheses and the tilde. Okay, or in between the tilde and the parentheses, it tells you what type of distribution it is. Binomial. Okay, and so I'm going to use bin to shorten that. Okay, and then you put the two parameters. N goes first, and then p for a binomial. So you have n comma p. You first put the trials, and then you put the probability of success. So, for example, if I wrote x tilde binomial 10.5, that would mean that x is a random variable that has a binomial distribution where there are 10 trials, and the probability of success for each trial is 0.5 or 1/2. Okay. And now we get to the interesting part. And that part is the PMF of the distribution. So this is before where we would use a table. But now it's a function. Okay, and so this is what the binomial PMF looks like. For a PMF, I'm always going to use f as a function. So it is a function, okay, and how we write this function, it takes in a value x, okay, and I already know it takes in x, and then it also takes in the values of the parameters as well. And then the actual functional form is on the right. And how you would read this, because you have not seen it before, this thing here is read as n choose x. N choose x. And so it's probably been a while, but you've probably heard of permutations and combinations. It's in this book, and we skipped over that section because we don't really need it too much. But we have n choose x, okay, p to the x, 1 minus p to the n minus x. And you may wonder how they sort of got this formula. And it's not too challenging to think about. So this second part here, p to the x, that's the probability of success raised to however many successes that you had. Okay, so the input of my function is the number of successes I had. The output is the probability that happens. Okay, so I have probability of success is p, and I raise that to the number of successes that I have. Okay, so that's how many successes that I have, that first part. And you multiply those probabilities together. It's raised to the power, so it's really p times p times p x times. Okay, and then, so that's the successes part. The second half, 1 minus p, represents the probability of failure. If p is the probability of success, 1 minus p is failure because we only have two possible things. And that happens n minus x times. N is the number of trials. X is the number of successes. So whatever is left over, n minus x is the number of failures. Okay, so we have successes, failures, and then n choose x says how many ways can that happen? If we look back previously up here at our simple one, tossing a fair coin 3 times, of course, x equaling 2 can happen, 2 heads, but how many ways? There would be 2 heads and 1 tail. How many ways does that happen? Well, it happens more than once, right? It's heads, heads, tails, heads, tails, heads, and then the third one would be tails, heads, heads. That happens 3 different ways, and so we need to take that into account. That's where the n choose x comes into existence. Okay, so anyway, that was a lot of discussion there. Hopefully that made it easier to understand. If not, it's fine. It's a formula that you substitute numbers in to get out probabilities. Now, what the heck does n choose x mean actually? Like, how do you calculate it? And I put that down here. N choose x is equal to n factorial divided by x factorial times n minus x factorial. So if you forget what factorial means, it's the number times every number below it. So 5 factorial is equal to 5 times 4 times 3 times 2 times 1, all the way down. Okay? So that's the binomial distribution. So let's practice using that PMF. Simple experiment here. I'm shooting free throws. So free throws in the sort of basketball sense. And if you don't know what a free throw is in basketball, Google it and it'll show you sort of what it is. Right? So I shoot a free throw. I'm unabated to the hoop. I stand a certain distance away and I shoot. Okay, great. I shoot 10 consecutive free throws, 10 free throws in a row, and the probability that I make any single free throw is 75%. With this information, we know that this is a binomial experiment. I have a fixed number of trials. Success or failure, I either make it or don't. Every time I have the same probability of success of making it, and the trials are independent, basically. Okay. Again, we could think of this problem and think of ways that it's not independent, but just bear with me. Okay. I'm not tired after 10 free throws, so I'm not getting tired, and it doesn't affect me whether I make the first one, whether I'll make the second one. Okay. All right, anyway, so we've got a binomial experiment here. We denote this, we'd say we're going to make a random variable that counts the number of successes. Rather, let me actually ask the probabilities. Find the probability that I make 6 out of 10 free throws. All right, so we need a distribution to help us find this probability. And the distribution is binomial. So x, which is counting the number of free throws that I make out of 10, is or has a binomial distribution. Trials 10, probability of success 0.75. So I'm going to find the probability that I make 6 out of 10 free throws. So in a probability statement, that's the probability that x equals 6. That changes to our sort of PMF functional form, f of 6, given that n is 10 and probability of success p is 0.75. The formula is n choose x, so that's 10 choose 6. Probability of success 0.75 to the 6th power times the probability of failure 1 minus 0.75, which is 0.25 raised to whatever's left over, the fourth power. Okay, and so then let's go through this tedious work of 10 factorial over 6 factorial times 4 factorial. Okay, it was n factorial, which is n is 10, over x factorial, 6 factorial, times n minus x, or 10 minus 6, which is 4 factorial. 0.75 raised to the 6th power times 0.25 raised to the 4th power. Okay? And so if we do this calculation, and I'm just going to do this with my phone that I have right now, and so it's going to take me just a few seconds. And the probability that I got after I did all this was 0.14599. So I'm going to say 0.146. Okay, and there's technically no guarantee that I'm correct here because I did it on my calculator and I'm not 100% sure that that's that, but you will want to check, okay, and make sure that you've got your parentheses good everywhere, so on and so forth. But we're actually going to check this later on in our video, so I'm not going to worry too much about it right now. But anyway, that's how we find a binomial probability with the PMF. All right, so here's a your turn. I want you to use that PMF to find this probability. So I flip a fair coin 5 times. Okay. Fair coin means 50% heads, 50% tails. So there's your probability. What's the there's the probability of any coin flip being heads, okay, or tails. What's the probability that 2 out of 5 will flip heads? Okay, so here's a question. 5 is easier. 5 is a lot easier to work with than 10, right? And so try to find that probability.